L, the angular momentum operator. So now he had asked that L, the angular momentum operator, it's a pseudo vector, which means that, so whether a quantity is pseudo or not depends on how it transforms under parity. Okay, so let me just make that clear. The pseudo nature is determined by its transformation under parity. So if you remember, parity is you take X and replace all the spatial coordinates by its inverse. And it's a discrete transformation, meaning that you cannot make this transformation by composing it with rotations. Just 1 second, okay? Okay, so under parity, of course, in normal vectors such as X or P, they change to negative of the vector. Okay, so of course this is by definition, and this is because P is m dx by dt, and t is not changing, so since x is changing, p is changing. And since L is x cross p, we have two normal vectors, therefore L is a pseudo vector. That under parity, it does not pick up a minus sign, okay? So if I transform with parity, this will, okay? So now, this is something I have mentioned before, is that, when you make a transformation of your system, you can take 2 points of view. You can take the passive and the active, or the active point of view. And if you are, say, looking at an operator, the way that an operator, transforms under a transformation of the system is by similarity transformation. So what do I mean? So suppose I do a translation of my system, okay? A translation, or say a rotation. Okay, so if I do this, then what happens is that our state psi gets, changes to a state psi prime, which is related to the original state by some unitary operator, which depends on the parameter of the transformation acting on the original state. But how do the quantum operators, change? So if X is a quantum operator, under this, under this transformation, this guy changes like U alpha dagger X of U of alpha. Sorry, it should be the other way around. It should be U alpha X hat U dagger. Why is that? Because one thing we expect is that if, for example, this is some kind of a, we are measuring, something like this. This is an observable and it's a scalar quantity. And under a transformation, a rotation or a translation of the system, this thing should not change. And if it doesn't change, then if I replace, psi by psi prime, then I must replace x hat by x hat prime. But if psi prime changes like that, x must be related to x hat, so this must be, x hat prime must be like that, so that the unitary operators on the right-hand side, they cancel each other and we get this. Is it clear why this is so? Because, I have over here, psi prime is psi u, and x prime is going to be u dagger x of u, and this is of course 1, and similarly something similar will happen here. So always remember that the way that quantum operators transform under some physical active or passive transformation of the system is via a similarity transformation by unitary operator. So this is known as a unitary transformation. Okay, and these two are together known as unitary transformation. Okay, so any questions so far?
So, sir, so basically it's not merely a change of basis. The operator itself is also being changed in this case.
Yes, it is a change of basis.
Is it just a change of
It is,
basis?
yeah. Can I show you an analogy that will make it clearer?
Yeah, of course.
So suppose you are in three-dimensional space. Okay, you're in three-dimensional space. And you have a position vector, like, let's call it, say, R. Now, suppose you rotate this position vector, with some, around some angle, say, so, and that is given by, say, some matrix called R theta, right? Acting on R. So this is going to be give you the new position vector, right? So, you rotate your system, you do an active transformation, say, and you get your R vector changes to another vector of equal length but different orientation, right? So this is matrix multiplication, meaning that if I take R prime I, then this is going to be Rij Rj, where there's a summation over J. Okay, is that clear, Nahi? That's clear, right?
Yes, sir.
Yeah. Now suppose that you say, okay, I was doing all of this in a coordinate system. So suppose this is your coordinate system, this is your y-axis, this is your x-axis, and there is a, say, z-axis, okay? Oh, sorry, z-axis, not prime. Now suppose, sorry, also this is not prime. Okay. And now suppose that you change your axis, right? So you change it to a new, coordinate system. So this is your new y-axis. So this is y prime. This is your new x prime axis. And say this is your new z prime axis, right? So this is a change of basis of your reference frame, right? So you're changing a reference frame, or you're changing the basis. So now you want to express, this equation. So this equation is independent of any basis because it's written in a vector language. But this is a component equation. So now you want to ask, how does this, okay, let me just change the notation a little bit because I want to use the rotated vector, I want to denote it by tilde, okay? So I want to denote the rotated vector by tilde, and you will see why. So now I want to express this equation in this new reference frame. How can I do that? What do you think, Naheed? So you know what? How R is going to change? So suppose that there is a rotation, say R prime, which changes my, X, Y, Z basis to X prime, Y prime, Z basis, right? So that rotation I'm calling R prime, okay? So given this, can you tell me how, this vector will change?
We know, since we know how R changes, we know how each of the components
So we
changes.
know how each of the components change, so we know how this changes, right?
Yes, sir.
So, under this base change of basis, what's going to happen is that R of J will go to R prime of J, and that will be related to R prime J K R K, right? And I'm going to use the Einstein convention, so repeated indices mean there is a summation, okay? Right, so you agree with this, right?
Yes, sir.
So, of course, this is going to be, there's a slight technicality, because this, this R prime matrix will be actually the inverse of this matrix, right? No, actually, it's fine. Yeah, sorry. I take that back. All right. So that's not important. So we also know that the left-hand side will also change similarly, right? The components of R tilde will also change in the similar way. So there will be, it'll change to R tilde of J, R of J, R prime K of R tilde K, right? Do you agree, Nahi?
Yes, sir.
Because everything, the whole thing is changing. So now if I look at this equation in this new reference frame, I will have R on the left-hand side, R tilde of I is equal to J 1, 2, 3, and some other R, let me call it, and here I will have R prime of, say, J. Again, so I'm not going to use this, and there will be a J here, and there'll be I here, and it'll be some new rotation, R. Now, my question is, how is this R bar, related to this? Can we figure it out? So on the left-hand side, we have from here R prime JK R tilde K, right? On the right-hand side, we have R bar IJ. Over here, I have R prime JK R K. Okay? So everything here is components, right? because there I've written the whole thing in terms of matrices. By the way, it's important to make sure that I didn't make any mistake, which I did, of course, because over here this should be ik, right? All right. Now I want to, what I can do is that I can apply to this equation the inverse of the R prime matrix here, right? So if I do that, the free index is I, so I will apply R inverse Li R prime I of k, R tilde of k, and on the right hand side I have, sorry, this is inverse, the R prime inverse R bar ij, this is Li, and here we have R prime j of k, R of k. Now, since this is the inverse, this is delta Lk. And there is a sum over k, which I do, if I do the sum, I get R tilde of L. So R tilde of L is going to give me R prime inverse Li, but we know that, yeah, that's fine. And then we have R bar I of j, and then I have R prime j of k, R of k. Now, this equation should be exactly this equation. So let me copy this equation and take it down below to compare. So I paste this equation, and then what I do is that I'm just going to get rid of the summation notation. So on the left, and then I'm going to just like change this indices, I'm going to call the left index L, and so this would be L, and this would be, I'm going to call it KK, right? So now we see that if this equation is going to be equal to this equation, then this thing must be equal to this thing. So you see that when we do a change of basis, the rotation matrix, the linear transformation, so linear transformation, right? The rotation matrix is a linear transformation. Do you agree?
Yes.
That changes in this form. So R goes to an orthogonal transformation, O inverse, because these are, as you know, these are orthogonal matrices, right? Or R transpose is equal to R inverse. So this linear transformation goes to O inverse R of O, which is a similarity transformation. So as you can see, when we do a coordinate transformation, when we change the basis, even in three-dimensional space, the linear operators also change. This is also part of change of basis, right? Do you agree?
Yes, sir.
So you see that when we are doing in quantum mechanics a unitary transformation, which involves a change of, like a unitary transformation on the state, we have to do a simultaneous transformation on the observables by a similarity transformation. So these together form a change of basis, okay?
Sir, in that sense, like, could you relate this to the time evolution operator? Because, like, the state evolves with time, and with the operator, then would we say that the operator is also evolving with time? in terms of a unitary transformation?
Um, in fact, exactly that's what happens if you go to the Heisenberg. In a sense,
Yes,
that happens
yes.
in the Heisenberg, picture.
But then again, in the Heisenberg picture, the state doesn't change. But in this case, both the state and the operators are changing. So that is basically the
Right. I
cause.
see. I see what you're trying to say. Yeah. Let me just think for a second. Okay. So what is the assumption here? The assumption here is that this expectation value is something that does not change with time, right?
Yes, sir.
Yeah. So in a sense, this is basically what we would call a you know you know a constant of. So okay,
Motion.
if it doesn't change with time, then this would be a constant of motion.
Mm-hmm.
Okay. So if
Yes.
it doesn't change with time, then basically, the operator that we are interested in under time evolution would essentially commute with the Hamiltonian. Okay? So we are saying that it actually is a very special kind of operator.
Okay.
But for general, for general operators, we are not saying that that expectation value is unchanged with time. Okay.
Sir, I was thinking in a way, could you just say whether it's correct? So I was thinking that if we by the action of some rotation operator we change the state. So at first we calculate the expectation value of the let's say the angular momentum, and then after we rotated the state and went into a new state, then again by sandwiching we again have another expectation value of the angular momentum. If we say that both of them are equal, then essentially we're saying that the angular momentum is rotationally invariant. So in this case, it's only the basis that is changing, I guess. Um, uh, like yeah,
Right. I mean, I think I see your confusion, and it is a little bit subtle there, because if I make a transformation change of basis, then you're going to say, okay, then Li should not change. But that's not what I'm saying. I'm saying that what should change is that if I change the basis, then Li should change like this. And if U is a rotation operator, then you will have the form of exponential of minus I, some angle, say theta, some direction vector n, and the L operator. And then what you have to do is that you have to basically work out using the commutation relationship between L with itself, what this thing is. And you can convince yourself that is going to be exactly Rij, where this is the rotation operator in real space, which depends on the direction n and theta acting on Lj. Okay, so this is a non-trivial exercise.
sir. Also, sir, won't Li commute with you because L is the generator here? No, sorry.
No, it won't, because
Yeah.
it's not L squared.
Mhm.
Okay, so all right, so I think we should probably move on, because um, we can come back to this offline if you have more questions, Nahi. But I think it's very important that what you're asking.